So okay, go please.
Okay, so in this second part, I will talk about boundary controllability of two-wave equations. So this time, two coupled wave equations instead of ODE system. And this time, the coupling will depend on space and time, and it is the first order coupling. So this work has been done with Ammar Koujafarid, is my supervisor, thesis supervisor. So I will start by some preliminaries, talking about a little bit about the problem and what has been done. And then I will define new concepts. Is the weak observability, is a weaker inequality or laxed one. And then I will finish by unique continuation property for the system. So the system in question is the following. So I will consider this system as this state, the y, has two components, y1 and y2. So this is the system. And the speed of the propagation equals to 1 to make more to make things simple. And this M is a matrix of size 2, square matrix, is the coupling matrix. And in front of each component, I will put the coefficients. This is the coupling coefficients A and B. By first order coupling, I mean that the coupling is a derivative. For instance, if we to be more clear, if we consider two equations, for instance, the first I will call y, and the second by z, and I try to couple these two equations. For instance, a zt plus b zx, and the second one plus a yt plus b zx yx. Sorry. And this is an example of two-wave equations, but the coupling is the coupling is first order. For zero order coupling, we have just to write z without derivatives. So this calls the zero order coupling. Sorry. And these functions, coupling functions A and B, will be assumed to be C1, and I will try to control this whole system, these two equations, with just one control that acts on zero. I mean that by one control, that the control matrix B is the form B1, B2, and has rank, the rank of B equals to 1. That means that we control both equations at the same time. For instance, if B1 equals to 0, and we control just the way the second equation, and this second equation will control the first one. And if I let B1 and B2 equals to 0, then we do the contrary. Y1, the control will control the first component, and the first component will control the second component. And I will put myself in this functional framework. So I know, according to some results, we can even prove it, that our system, this system, is well posed in this setting. The control U is in L2. The second component is in the dual space of H10, and the Y0 is in L2. And you know that there exists a unique solution Y in C0T, this space here. So I will call you some classical definition. So our system is exactly controllable at time t if for any initial states and for any target states in this space, energy space, there exists control U such that my solution at this time, capital T of control, equals to the target state. This is just the definition of exact controllability that we have seen in the previous slides. And for the approximate one, I will repeat the definition. So for any Y0, Y1, Z0, Z1 in this energy space, and for any neighborhood, of the target state, I can find or control U in L2 such that the solution Y or YT to system S satisfies this this identity, or so the distance between the target state and our solution is less than this epsilon. So what has been done in this type of problems? I'll start by some works of Alabou and Lioto. They studied boundary and distributed controllability both for zero couplet. So the coupling here is zero, is of order zero of all equations. And the assumptions and the coefficients, they assume that the coupling coefficients, the A and the B, are small, are sufficiently small in the affinity norm, is less than some delta, sufficiently small, and this coupling coefficients are of constant sign. That means that either the A or the B are positive or strictly negative. This last assumption of the size coupling coefficient has been get rid of in this work by Lioto, Lorousseau, and Dehman in 2014, and it left just to deal with this constant sign coupling function. I don't know whether it is optimal or not. For the constant case in this zero order coupling, there is some results, and the Kalman condition is necessary and sufficient for controllability for the constant case. And for the in the distributed control case, if we take, for instance, this wave equations, this system plus A, this the coupling matrix, plus some controlled here BU. And so if this system is controllable if and only if this matrix, the Kalman matrix, has a rank n, which is the same number of states. For the boundary control, the problem is more harder, and in the constant case, we have a full answer. We have to add, the Kalman condition is necessary and sufficient, but we have to add some other assumptions. For instance, some assumptions under eigenfunction or eigenvalues of the associate operator of this operator, Laplacian plus A, to make sure that we have exact controllability. So concerning the first order coupling, there is some results of Ben-Nour and Ammar Kouja and Tignou. This is from 2017, where they studied this system, I'll write down, plus chi of x, this time dependent x, and the coupling is for order 1 and the velocity Tt equals to the xx. And we assume that these two states satisfy the Dirichlet condition and the boundary, except under zero, in the zero for zt equals to ut. So I control z and x equal to 0, and this z we control y through this component here. And they proved that the necessary and sufficient condition is that the average of A of x dx must be non-zero, plus the minimal time of control, of course, plus another condition for absolute controllability. But the most interesting one is this condition. Recently, Laurent, Wang, and Cui, they consider more general systems in more general settings, but always with periodic boundary condition in 1D, because they worked on Riemannian manifold without boundary, and they proved that they gave only sufficient condition in the constant case, which is already known as the Kalman condition. And weak controllability result, I will go back to this later, in the space-time coupling case, but always with periodic boundary condition. So the main goal or the aim of our work is to find a necessary and sufficient condition for any type of coupling. I will go back to our system. Sorry. So our system is general, as you can see, and we have to find the optimal conditions that should A and B satisfy so that the system is really controllable with less number of control. Okay. With a little of computation, we can show that the adjoint problem, it's exactly like as explained in the first part of this talk, that the dual problem of system S is given by this system here. So the derivatives are transferred now to the phi instead of the whole A phi. It was, for instance, like that. If we multiply by z and integrating by part, then we obtain y a zt. And this is the dual problem. And I will call A index t, capital T, by A t minus t, and the same thing for B. These are just on notation. In this case, the LT, the adjoint operator of control, LT, the initial state, this time, equals to B start, the adjoint of the vector B of phi. I will take the derivative and the trace and 0. This is, of course, an operator which acts from this space to L2 0t for the control leaves, which take the initial state to this solution to adjoint problem. And I know that this adjoint problem is well posed and everything is okay, and the trace and 0 exists. So everything is okay from a well-posedness point of view. So there is nothing to do here. You can prove it, for instance, by semi-group theory. And I will tell you some definitions. System S is exactly controllable at time t if only if the adjoint system or the dual system is exactly observable. So this is just the observability inequality. This is our V, and this is our LT or adjoint of our input map LT. And the second definition is definition of approximate controllability. As we have seen, approximate controllability is equivalent to the unique contention property. So if this operator LT initial state V1 equals to 0, does that entails that the initial state equals to 0. So this is just an expression which is equivalent to this statement here. Now I will define what we call this weak observability inequality. So we will say that as start or our dual problem is weakly observable at time t if the observability inequality is satisfied. But this time we add some term here where this n is compact operator from our energy space to L2 0t. So this kind of a relaxed inequality or a more weaker form of the observability inequality. We can see that if n equals to 0, then we fall under classical observability inequality. And two interesting consequences of this observability inequality is that if this inequality is satisfied, then the space of target state is finite codimension. That means that if we start from, for instance, space E to F, then my LT, then I don't know if I can reach all the F or not, but I am sure that I can reach a finite codimension space, subspace of F. And to make sure that we can reach all F, so all the energy space, we have to add, or we have to prove the unique continuation property for system S, or S start. So weak observability plus unique continuation, that entails the exact observability. That means that if we prove these two guys, then this term will be or will disappear. Okay, so I will start by the first negative result. If T is less than 4, which is the minimal time of controllability, then our system as start, or the dual system, is not weakly observable, excuse me. That means that there exists a space of finite codimension of target states that I cannot reach. And this is so intuitive because for one equation, for instance, the minimal time of controllability is T equal to 2. This is because this equation can be decomposed into two transport equation, T minus Z plus ZX equals to 0, for instance. And each equation requires 1 as minimal time. So 1 plus 1 equals to 2. And solid wave equations requires T equals to 2 to be controlled. And since we have two wave equations coupled, but with one control, so 2 for each equation, and for the whole system is 4. So this is so intuitive time of controllability. Now, if we assume that the T is larger than 4, the control time, I need to introduce some notations. I will start by introducing this function phi, which is defined from phi from 2 capital T, which is greater than 4 of real valued function. And this phi is defined by integrals. What are these eta plus and eta minus? They are our coupling function, A index T. I will recall you that A index T is equals to A of T minus T, X, and the same for B. So this eta plus is the A T plus BT over 2. And the eta minus is AT minus beta index T over 2. And I take these two functions and I integrate them over 0, 1 on these curves. Okay, so let us talk about the geometric meaning of this phi t. Let us fix, for instance, some t here, because this is the t-axis and this is the x-axis, okay? And the curve that eta minus is defined over this curve, that means that I take some t, I go back through this line of slope 1, or slope minus 1, sorry, until t minus 1, 1. If I integrate eta minus and this line, I get this term. And now I will go back with a line of slope 1 to x equals to 0. And this is exactly the curve here that we are integrating over. And this gives, and that means that this phi t is the integration of the coupling functions, new coupling function, I mean, eta minus and eta plus, over these two curves. So I will take, for instance, some t here. I will integrate over this curve to x equals to 1, eta minus, and I will go back to x equals to 0. Okay, let's say that t equals to 0 x. I will go back to x equals to 0, and this is as you can notice that this is the reflection of the rays that start from the control region, because we control and x equals to 0, and it is reflected on the boundary and go back to x equals to 0. Okay, so I will start by the first results or interesting results to us. It is a weak observability result. Let lambda 1 and lambda 2 be in the spectrum of M start. If M is diagonalizable matrix, and by this mu, if it is Jordan, for instance. And let N be larger than 2. And I will take this first time T to be between 2N and 2N plus 1. For instance, we can think of N equals to 2, and we take T equals to 4. This is the minimal time of controllability. Then system as start, or the dual system of our initial system S, is weakly observable if and only if these three conditions are satisfied. The first condition is the Kalman run condition. That means that the coupling can pass from each component to the other. This is necessary condition. And the last two conditions are about the integration of our coupling function along characteristics. For instance, for the second, for each x in 0, 1, I should find k between 1 and n minus 1. We can always think of n to be equals to 2, and in this case to k equals to 1. Such that if our matrix is diagonalizable with 2 real eigenvalues, or it is Jordan, for instance, we have to assume that our coupling function, the integral of our coupling function, or the phi, are not 0 for any x between 0 and 1. And the second condition is the same condition, but with some shifting here. We can always think about the case n equals to 2. For any x in 0, t minus 2n, if I take t equals to 4, for instance, and this 4, so this will disappear, and we work only with x star. So for any x in 0, t minus 2n, and x start between t minus 2 and 1, so the 0, 1 is now decomposed into two parts. That exists a k between 1 and n, which corresponds to the k to this case, and k start between 1 and n minus 1 is just exactly as the first case, correspond to the x star, such that my function phi doesn't equals to 0, and phi xt plus 2k star doesn't equal to 0 if our eigenvalues are real, or our matrix complement is Jordan, and they are not in the discrete sets if they are complex. I forgot to talk about this second condition. If the eigenvalues are complex, our matrix is diagonalizable, and these two eigenvalues are complex, then this assumption becomes as the following. These integrals, or other integrals, if x varies between 0 and 1, should be not in the discrete set. This is the imaginary part of lambda 1. And since these two eigenvalues are conjugate, they have the same imaginary part, so we can take lambda 1 and lambda 2, and it is not important. So what we can conclude here, that the Kalman condition is a sufficient condition, and we have to add some assumptions and the integrals over the characteristics of the coupling functions. The same results hold true if t is between 2n plus 1 and 2n plus 2, with slight modifications at the level of the of X and X star. I also want to make a remark here, is that since our system is non-autonomous, so the coefficient depends on time, we have at each time t a sufficient and necessary condition. This is not exactly, it is not as for the autonomous case. If we have controllability, then it's okay, it is necessary and sufficient. But for the non-autonomous case, we have at each time a condition for controllability, as we can see here. Okay. So I will make now a little link or little remark between the parabolic case and the hyperbolic case. First of all, if A and B doesn't depend on time, then this phi t is independent of time, of t, and it is just the average of A. I will go back. I explain why this is possible. If the coupling function are independent of x or t, excuse me, then this part will disappear, this part will disappear, and it plus bt, it minus bt, this bt with this bt will disappear, and it left 2 it over 2, and at the end I will obtain the average of A over 0 over my domain. So there is a very interesting remark here. It states that we cannot use the component byx as coupling in the autonomous case if the coefficient doesn't depend on time. Since in this case, if for instance we let A equals to 0 and we depend only on B, then there is no controllability at all unless B is time dependent. So this phi will equals to 0, and as we have seen in this theorem, phi doesn't should be 0 at all, which are necessary conditions.
Yes, yeah.
Yes.
Yeah. Okay. Just maybe you may focus only on the essential result because it stay 10 minutes.
Okay.
Yeah.
Okay. So I will pass this slide, and okay. I will pass the proof. I will not talk about the proof.
Yeah.
Okay. Now, as I have said before, for the weak observability, to make sure that the rest of the target states are controllable, we have to make sure that our system or the unique continuation property holds true. I will start by results in the constant case. Assume that A and B are constant. Then we have two cases to consider. The first, when M is diagonalizable, the unique continuation property holds true if and only if this identity holds true for any N1 and 2 in Z. And this assumption here guarantee that there is no invisible state. Then in addition of weak observability, we can reach any states in the state space. And if have only one eigenvalues of geometric multiplicity 1 or 2, for instance, then the condition becomes more simple, and the condition depends only on A, B, and the mu, and the eigenvalue of this matrix in this case. Okay, so in the autonomous case, I will pass. There is some criterion, it's which called the Fatony Criterion, which gives a sufficient condition to ensure that there is no invisible state in the target in the space of target states. And this condition, sorry, I will go back to it's sort of perturbation argument. If we have two systems, for instance, Y1 and Y2, and the second system is is a compact perturbation, or is a bounded perturbation of the first one. So to transfer the property of controllability from the first non-perturbed one to the second, we have make sure that the difference between the two control maps, these represent the LT, these are the LT1, LT2, is compact for some T, and the kernel of this operator here, S minus I to start, the perturbed one, enter the kernel of the control operator with the same notation, this B start, is void for any S. Then we can conclude that the second system is exactly controllable. Now we will apply that with this criterion on our system, and we find a condition for finite dimensional one. That means that to guarantee that there is no invisible states, we have to make sure that the rank of this matrix here equals to 4, which is the number of our transport equations. We have 12 equations, and each of them can be decomposed into two transport equations. The rank is 4 for any S in C. This R is the fundamental matrix of this finite dimensional system. It's just a finite dimensional system that we have to solve and to find the conditions and this rank of this matrix. These two matrices, C0 and C1, are defined by this formula. It is too difficult to find unnecessary sufficient conditions, or the fundamental matrix, since it is a complicated system, but it might work for some particular case of M. For instance, if we take M 0, 0, 1, 0, for instance, it can work. Okay, so this criteria gives sufficient condition to make sure that there is no invisible states, but it works only for the autonomous case. In the non-autonomous, autonomous case, there is some results. I will pass the proof. Okay, I will just take about the case, very particular case for unique continuation. The first case is, let us assume that our new coupling function eta plus and eta minus are of this form, are equals to some function alpha who depends on t, and x is in this particular form, and the second is beta t plus x. In this case, we have a sufficient condition. Let me introduce these functions ace1g and ace2 index g, which are defined in function of the average function phi and these new functions alpha and beta. And we can observe that it involves now the derivative of phi. And the result is the following. If we let n larger than 2, it means that I take t greater than 4, and assume that, this matrix is invertible. I will go back to the matrix, This matrix here is invertible. That means that this phi are not 0 for any x. So this just as first condition. Then the unique continuation property holds true in time t equals to 2n. This is just a particular case. We can generalize that, no problem. If the averages of these two functions are not equals for some k and l. So everything happens under averages of these coupling functions. The second case is more simpler. This time, what is the proposition? Okay, this time I will assume that the contrary of the first case, I will assume that this alpha is defined, the eta plus, it is alpha t minus x, and I will put here t plus x. I forgotten to write. And this time we have a necessary and sufficient condition. If our average functions phi are not 0 for nx and 0, 1, then the unique continuation properties hold true in time t equals to 2n, if and only if 1 is not an eigenvalue of this 2 times 2 matrix. This kernel n, it is given later, I think. Yes, this kernel actually, it depends on phi, the element. I forgot. So this k is k11, k12, k21, k22. If and only if 1 is not an eigenfunction or eigenvalue from of the average of this matrix, which depends on x, or the integral of this matrix. And thank you for listening. I think that I am out of my time.
Thank you, Yacine, for this nice talk.